Welcome back, Physical Science. This is the second video to correspond with the booklet 6.3 Heat Capacity in the HT1 section. So we looked at specific heat capacity for the first part. Now we'll look at the second half, the principle of thermal energy exchange and potential problems that could happen with that. So things to highlight here. The principle of thermal energy exchange states that whenever a warmer object comes in contact with a colder object, thermal energy is transferred from warmer objects to colder objects until thermal energy is evenly distributed in both objects. So heat goes from hot to cold until they both achieve the same temperature. If you use a quantity of heat equation to calculate the thermal energy released by the warmer object, or Q released, and the thermal energy absorbed by the colder object, or Q absorbed, the two values are equal in magnitude and opposite in sign. So we assume that it's 100% transferred and not thinking that there's heat loss, even though technically there would be. But we'll assume that all of that heat is transferred. So Q released would be a negative since its temperature is going from a high temperature to a smaller temperature. Q absorbed would be positive since the change in temperature would be positive, starting off at a low temperature, achieving a high. Considering the law of conservation of energy, this makes sense. Thermal energy, like all other forms of energy, cannot be destroyed. It can only be transferred or transformed in this case. Thermal energy is transferred from a warmer object to a cooler object. So this conclusion assumes that the thermal energy remains in the two objects being studied and not released to the surroundings, so we're assuming minimal loss there. In most circumstances, however, some is released, lost, etc. So mathematically, Q released and Q absorbed should add up to be zero because what is released by one object is gained by the other, negative, positive. So negative 10 joules, positive 10 joules equals zero. Or we can say Q released is equal to the negative of Q absorbed if we take it to the other side. So here we're looking at a couple of examples using this idea. Of course, Q is equal to MC delta T, so we can use that to break this down further and answer a few questions. So if you look at example 1, a 60 kg sample of metal is heated to 100 degrees C before placed in 200 mils of water. And that water has an initial temperature of 10 degrees. The metal-water combination reaches a final temperature of 15.6. Determine the identity of the metal. So of course you could do some CSI investigations here, determining the identity of an unknown metal by simply doing a heat transfer. And then with that, whatever we get for a value, we can go back to a chart like this, look at the specific heat, and identify what the metal is. So a very sneaky way of identifying what a metal would be by using a heat transfer question. Okay, so if we get back to the question here, so we need to know MC delta T and MC delta T for both the metal and the water. I think we do here. We know it's 60 grams, so I use a little subscript M for metal, a subscript W for water, so we know the mass of the metal, 60 grams. Or, of course, since when we're using this equation, our specific heats are in joules per kilogram degrees C, we have to make sure our masses are in kilograms as well if we're using that specific table. So, of course, 60 grams, move the decimal 3 places to the left, decimal 0600 kgs. The initial temperature was 100. The final temperature is 15.6, so we'll take 15.6, subtract 100 eventually to get the change in temperature. And yes, we don't know C of the metal. We don't know the specific heat capacity because that's what we're asked to find out. Water, we know it's 200 mils. Since water has a density of 1 gram per milliliter, 200 mils is the same thing as 200 grams. Divide that by 1,000, so it's going to be 0.2 kgs, as you can see down here. So 200 mil, or you don't have to do this calculation if you remember that it's water. Density is 1 gram per milliliter, so 200 mils is 200 grams. Then divided by 1,000. The water was at 10, went to 15, so 15.6 minus 10 will give us our difference. And the specific heat for water, 4.18 times 10 to the 3 joules per kilogram degrees C, as you can see from this table. All right, so we know everything except the C value for the metal. So if we use this idea that Q released plus Q absorbed should all add up to be 0, we can represent that as, instead of Q MC delta T and MC delta T. And to keep them separate, I use a subscript M, so MM, CM, delta TM, all for metal, MW, CW, delta TW for water, and then just simply substitute everything in. So the metal, 0.06 kgs, the C value we don't know. Final minus initial, you should always get a negative value here because the metal is losing energy. Plus the mass of the water, specific heat of water, and the temperature change of water, 15.6 minus 10. So multiply all this out here. So first of all, 15.6 minus 100 is negative 84.4. 15.6 minus 10 is 5.6. And then when we have that, this times C times negative 84, or just simply multiply the two numbers first, I get negative 5.064 times C. 0.2 times 4.18 times 10 to the 3 times 5.6, I get that. That'll equal 0. Then it becomes like a grade 8 or grade 9 math manipulation question. So we have negative 5.064 times C plus 4681.6 equals 0. So to isolate C, I need to isolate this whole section first of all. So subtract 4681 from each side. And I get this, negative 5.064 times C equals this. Then to undo multiply, divide each side by negative 5.064. And of course this will work out nice because a negative divided by negative will give us a positive, which is what specific heat needs to be. And I get 9.24 times 10 to the 2 joules per kilogram degree C. And if we had a table that listed tons of these, we could actually find the identity. I don't think that particular one is listed on this table. Let's see, 9.24. Oh, it might be. It might be aluminum there. I think it was 9.2 times 10 to the 2. If it was, it could potentially be aluminum. And yeah, it could very well be. Oh yeah, and I guess I mentioned it there too. So, all right, other things we could look at here. So using that idea of the principle of thermal energy exchange, sample of iron is heated to 80 degrees C and placed in 100 mils of water at 20 degrees C. Final temperature of the mixture is 22 degrees. What was the mass of iron? So here, I'm told the identity. I'm told it's iron. So you can go back to this table here and actually look up the value of iron. There it is, 4.5 times 10 to the 2. So we know its value for C. Liquid water, we know that, 4.184 times 10 to the 3 joules per kilogram degree C. So we know everything here. So the mass of water, 100 mils, which is 100 grams, which of course is 0.100 kgs. The temperature of water was initially 20, but it raised up to 22. The C value of water is that. And then for iron, we know the initial temperature is 80, final temperature is 22, and its value from the table is that. So again, Q released plus Q absorbed equals 0, or represent Q as MC delta T and MC delta T. Again, I have my metal, or since I know it's iron, I use a little subscript I here, and then of course water, and then substitute everything you know. We don't know the mass of iron, but we know its specific heat capacity, the temperature change, the water mass, the specific heat capacity of water, and the temperature change. So we know all the information, so we can take 22 minus 80, we get negative 58. 22 minus 20, we get 2. Then multiply this all out, 4.5 times that, we get this number. 0.1 times 4.18 times 10 to the 3 times 2, I get that, all equals 0. So of course, take this to the other side by subtracting it from each side, and I get that. And of course, since this is multiply here, divide each side by negative 2.61 times 10 to the 4, and I get 3.2 times 10 to the 2 kgs. So the mass of iron is 3.2 times 10 to the minus 2 kilograms. Okay, we'll call it quits there. We'll go through one more example, a few practice questions, and then we'll look at the assignment. See you soon.